Good evening, everyone. My name is Jack Doerner, and I'm going to be talking to you tonight about scaling ORAM for secure computation. This is joint work undertaken with my advisor, Abi Shalat. And the problem is a classic one. So we wish to enable multi-party computations to have access to random access memory. Specifically, we wish to build a system such that multi-party computations can read a single element I from some larger array of n elements in such a way that none of the parties to the multi-party computation learn anything about the index I. And this is, in fact, a very important and indeed necessary primitive. Consider this broad class of algorithms: graph algorithms, greedy algorithms, dynamic programming, etc. In order to implement any of these efficiently in the context of multi-party computation, you have to be able to do accesses to memory locations that are derived from intermediate results that you can't reveal to any of the parties. Unfortunately for us, however, multi-party computation protocols tend to be circuit-based, and circuits are not random access primitives. So the traditional solution was just to wire the circuit to touch every single element in the memory on every single access that you performed. And this is simple, it works pretty well. The problem is that it incurs an O of n complexity for multi-party computation, and this makes it extremely slow. Ostrovsky and Shoup proposed an alternative, which is what I will call memory gates. That is, the bulk of the computation is still done by regular circuits, just as it always would have been. But these circuits are interspersed with special gates that can perform random accesses. And inside of these memory gates, we find, not surprisingly, ORAM. Specifically, the multi-party computation protocol implements an ORAM client or translator algorithm as a circuit and uses it to issue memory instructions to an ORAM server being run by one or more of the computation parties. The idea being that the ORAM security properties will protect the multi-party computation against a malicious computation party who's observing the memory accesses. Unfortunately, getting good results from this construction isn't as simple as just plugging in any generic ORAM and hoping for the best. This is because traditional ORAMs designed in the outsourcing setting tend to optimize for the wrong parameters. They often optimize for client-server communication or perhaps server overhead. But in the multi-party computation context, the client itself is being implemented by an MPC protocol, which is being evaluated over the network. And consequently, you have to pay both computation and communication costs proportionate to the circuit size of your client algorithm. And those can be pretty substantial. This was first observed by Wang et al., who implemented path ORAM in the multi-party context. They later proposed SCORAM, a derivative of the tree ORAM schemes, with a heuristic eviction method that resulted in significantly reduced concrete circuit sizes. Wang et al. Later followed this up with circuit ORAM, which offered nearly optimal asymptotics while also further reducing the concrete circuit size. And unfortunately, while these are really significant improvements over the naive method of just using any ORAM you like, I contend that at least in the context of secure computation, we can do better. Specifically, circuit ORAM still suffers from relatively high constants. In fact, in our benchmarks, we found that it was slower than the trivial linear scan for memories of up to 2 to the 12 elements. We're still, however, to initialize a tree-based ORAM, you have to write into each element individually. And this means that for an ORAM with an access time of only 1/10 of a second, you have to spend over 10 minutes filling it with initial data. And this, in turn, means that you have to do thousands upon thousands of accesses before you have any hope of competing with linear scan in practice. Where do the high constants come from? Well, in the context of tree-based ORAMs, they tend to come from two factors. First of all, tree-based ORAMs have to overspecify their memory in order to avoid overflows. And eventually, you're going to have to read all of that overspecified memory. Second of all, tree-based ORAMs tend to have many layers of recursion, and this is necessary in order to guarantee good asymptotics. Fortunately, not long after the development of circuit ORAMs, Zahir et al. Had the insight to abandon asymptotics, proposing a derivative of the original Goldreich and Ostrovsky square root ORAM with an access cost of square root n log cubed of n. And although this is significantly worse than any of the tree-based ORAMs, it nonetheless yielded significant performance improvements in practice. They were able to push the crossover with linear scan all the way down to 2 to the 7 elements and continued to outperform circuit ORAM all the way up to 2 to the 18 elements. Furthermore, because their scheme had a special bespoke initialization method, they were able to fill their ORAM with initial data 100-fold faster than can be achieved with circuit ORAM. And this meant that their scheme was significantly more attractive for algorithms where only a small to moderate number of memory accesses would be performed. We intend to take this kind of reasoning slightly further. In fact, today I'm going to propose to you an asymptotically pessimal ORAM. That is, an ORAM with access complexity in O of n. This is, in fact, just as bad as the linear scan that we started with. But we'll be using techniques for private information retrieval to outsource this access complexity to each of the computation clients individually. Meanwhile, the secure computation complexity will be reduced to a relatively small O of square root of n. Furthermore, for accesses where we can publicly reveal the accesses to be reads and not potentially writes, we can do somewhat better, reducing the multi-party computation all the way to a constant. And for accesses where we are allowed to reveal the index that we're accessing, perhaps your algorithm has some number of deterministic accesses interspersed among the data-dependent ones, we can reduce the local complexity to a constant as well. Finally, our scheme will have an efficient initialization method that allows it to fill it with initial data with only constant overhead and with no multi-party computation whatsoever. It should be noted that although our access and read complexities are in some sense as bad as you're legally allowed to do, any worse and you're worse than the trivial solution, our semi-private and initialization complexities are actually optimal. Furthermore, all of this can be achieved in constant rounds. So, how do we intend to achieve this? Well, our ORAM is based on 3 primary principles. First of all, we lay out all the data in memory linearly. That is, there's one copy and it's in order. This means that we require no permutation map, no recursion, no shuffling, and because there's no chance of an overflow, we don't have to over-provision our memory. Second, we use private information retrieval to outsource the scanning to the individual parties. Using recent and exciting developments from this field, we can do this with only log-n computation and log-n communication and no public key operations. Furthermore, because the server component of these PIR schemes will be embarrassingly parallel, we can accelerate the offline component almost arbitrarily just by throwing more hardware at the problem. Finally, we will develop an efficient refresh operation that allows us to refresh our ORAM with no multi-party computation whatsoever. This reduces what would otherwise be a rather expensive amortized cost to something so cheap that, in fact, it's basically undetectable in practical benchmarks. In addition, our refresh operation will also allow us to initialize the scheme. So, the exciting primitive on which our entire scheme hangs is function secret sharing, recently developed by Boyle, Gaboe, and Ishai. Our scheme is, in fact, so dependent upon this that we've chosen to call it function secret sharing linear ORAM, or FlowRAM for short. What does it all add up to in practice? Well, we executed a simple binary search benchmark in which we loaded sorted data from an array into an ORAM and then performed a number of set inclusion or binary search operations upon it. And in fact, we were not able to find any combination of parameters for which any other memory primitive could beat ours. Furthermore, for some specific combinations, those in which we did only one search on the data, we were able to outperform the best previous solution by factors of hundreds. This allows us to search through roughly half a gigabyte of data in only 11.5 seconds. Bear in mind, this is in secure computation. Now that you're all excited, however, there are a couple of caveats that I should mention before I continue. First, this work is done in the semi-honest two-party setting, using Yau's garbled circuits as the concrete MPC primitive. But we don't believe that any of these limitations are inherent, and we expect that they can be overcome in future works. Second, the scheme I'm going to be talking about is technically a distributed ORAM, which means that although it is secure against the corruption of any single party that's participating, it's not secure against the corruption of all of the parties that are participating. This is, in fact, the same security model as multi-party computation itself. And if you're doing multi-party computation, you have to accept this security model regardless of the ORAM scheme that you intend to use. So, as I said, our scheme will be heavily dependent upon function secret sharing. And specifically, we're going to rely upon function secret sharing for distributed point functions. A point function, of course, being a function on some well-known domain, which is 0 at all locations on that domain, except for some particular location, here denoted alpha, at which it has a magnitude of beta. And a function secret sharing scheme for a distributed point function is a pair of algorithms, a generator and an evaluator, which work in the following way. The generator is given a description of the point function to be shared and also a security parameter. And it can efficiently translate these into a pair of function secret sharing keys that can then be passed to 2 other parties, here Alice and Bob. Alice and Bob can use these keys in combination with the evaluator algorithm to reconstruct a share of the output of the original distributed point function at any point in the domain of that function. These shares can, of course, then be recombined to reconstruct the output of the point function itself. A function secret sharing scheme is required to adhere to 2 important properties. First, correctness. At any point in the domain of the original function, the output of the evaluator algorithms must XOR together to yield the output of the original function. And second, security. It must be possible to simulate the function secret sharing key without access to a description of the original point function. Specifically, it must be possible to simulate the key using only the security parameter, the party index to whom the key belongs, and also knowledge of the domain of the function. So, it's going to be important that you all understand how function secret sharing can be instantiated. And in order to do that, we're going to focus on a specific case. We're going to focus on the case of a point function with a domain from 1 to 8 that's 0 at all points in that domain, except at x equals 5, where it's going to have a magnitude of 1. And for clarity, I'm going to illustrate the evaluator algorithms and the generator algorithm simultaneously. But bear in mind that these may be run asynchronously in the wild. Alice and Bob are each going to start with a unique uniformly random seed. And note here I'm using these colored boxes to denote values that appear random relative to one another. Additionally, the generator is going to begin with both seeds. Alice and Bob will also have access to some pseudo-random generator with a stretch factor of 2. And they can use this in a fairly standard way to construct a tree such that there is one leaf in the tree for each point in the domain of the original function. Now, bear in mind, these leaves can be thought of essentially as secret shares of a random value at each location. But what we desire is that Alice and Bob should have secret shares of 0 at every location. That is, identical shares, except for location 5, where they should have shares of 1. The generator can effect a transformation for Alice and Bob in the following way. Bear in mind that because it has both of their seeds, it can predict any value in either of their trees. So, it begins at the top level, predicts both of their values, for both Alice and Bob, and then generates a special correction value that it can send to Alice and Bob independently. Alice and Bob then apply this correction to both halves of their tree, and something interesting happens. On the half of the tree along which the path to element 5 does not lie, Alice and Bob's values become equal, and therefore all of their descendants in the tree also become equal. On the side along which the path to the element 5 lies, on the other hand, the values for Alice and Bob are simply re-randomized relative to one another. The important thing is, though, that Alice and Bob don't know which half of the tree was made equal and which half was re-randomized. Note here that the gray boxes mean that Alice and Bob still see uniformly random values, they just see the same value in each location. So, proceeding on, the generator can repeat this step at the next level, predicting Alice and Bob's shares along the active branch, and then computing some correction factor which it can send to both of them. And they're going to apply it to all 4 elements this time. On the left-hand half of the tree, of course, they already have the same values, so applying this correction will make them continue to have the same values. On the right half of the tree, on the other hand, we'll see the same effect as above applied again. In short, one half of the tree is made equal for Alice and Bob, and the other half of the tree is simply re-randomized. This process is finally repeated on the last level, yielding shares of 0 at all locations except for location 5, where Alice and Bob now have shares of some random value. The generator can cause them to have shares of 1 by repeating the process one final time, this time with no pseudo-random generator expansion, correcting their leaves at that location such that they have secret shares of only 1. Now, this function secret sharing scheme is really, really neat because the size of the keys that you have to send to Alice and Bob in order for them to generate these entire trees is proportionate only to O of log n, and of course the security parameter. And additionally, the computation that's required to generate these shares is also only O of log n. Unfortunately, if you try to instantiate the generator algorithm inside of multi-party computation, as we'll need to do in a minute, you're going to find very quickly that this suffers from rather high constants. And that's because the generator algorithm has to traverse down the active path of both Alice and Bob's function secret sharing trees. This means that it has to evaluate log n copies of PRG. And since our PRG is instantiated by AES, this can be rather expensive. So let's return to the function secret sharing tree and see if there's something we can do about this. Specifically, let's look at this one level. Now, at this point, the generator is going to need to generate a correction value for Alice and Bob. And this correction value is going to be based on the difference under XOR between either the left children of the active branch or the right children of the active branch. But notice that all of the other values at this level that are owned by Alice and Bob are identical. So, for instance, if we XOR any of Alice's values together with the corresponding value from Bob, they should cancel each other out. Consequently, here's what we can do. Instead of running a pseudo-random generator inside of the generator function, we can run the generator algorithm and the evaluator algorithms simultaneously and in lockstep. And when they arrive at this level, we can allow Alice and Bob to do the PRG expansion locally. They can then sum up all of their left elements and all of their right children under XOR, and then pass those sums to the generator, which can calculate the differences between them, and thereby calculate the correction factor, which can be applied, again, to Alice and Bob's trees. Now, given this scheme, how can we use it to read data inside of multi-party computation? Well, it's really quite simple. Suppose that Alice and Bob begin with identical encryptions of the data that they wish to read from. And the secure computation begins with some private index I that Alice and Bob aren't allowed to learn, and also the encryption key under which those two copies of the memory are encrypted. The generator function, or the multi-party computation, simply runs the FSS generator on a point function that has a magnitude of 1 at index I, and then passes the FSS keys to both Alice and Bob. Alice and Bob can then reconstruct the output of the point function at every point along the memory, and finally take the dot product of those output shares with the memory locations. Passing the dot product back to the secure computation allows the secure computation to XOR the two dot products together, producing a copy of the encrypted memory at location I. This can then be decrypted using the encryption keys that the secure computation was given at the beginning. Now, the reason all of this works is because at every location in the distributed point function other than index I, Alice and Bob have shares of 0. And therefore, the contributions from the memory elements at those locations cancel each other out. At memory location I, however, Alice and Bob have shares of 1, and therefore the contribution from that memory location remains. Now, this scheme is nice. It's actually very efficient. The problem is we can't write to it. And this is roughly the same problem as Goldreich and Ostrowski and later Zehur et al. Encountered when developing their variants of square root ORAM. Indeed, our solution will be very similar to theirs. We're going to use a stash. That is a small segment of memory into which we write elements as they're being updated, and from which we later remix these elements into the main memory. The problem, however, is that the remixing process, called a refresh, is rather expensive. And this is because we have no guarantee on what elements will be in the stash or what order they'll be in. So it's not possible to perform a refresh in less than O of n log n secure computation complexity. And this is a lot. We'd like to avoid this. Fortunately, we have an alternative method. We reuse the function secret sharing scheme previously described to duplicate updated elements into an additional write-only memory. We can then convert this write-only memory into a read-only memory with only constant overhead and with no multi-party computation whatsoever. This conversion process, of course, will also allow us to fill our ORAM with initial data. So we can learn to write in the following way. Suppose this time Alice and Bob begin with XOR shares of their underlying memory, and the secure computation begins again with some private index I, and this time with a value v delta, which is the difference under XOR between the value currently in the memory at location I and the value that we wish to write into the memory at location I. The secure computation runs the FSS generator function on a point function that has a magnitude of v delta at location I, and then sends the FSS keys to both Alice and Bob, who can reconstruct their function secret shares at every single point along the memory. Alice and Bob then iterate over the memory element by element, XORing those shares into the shares of the memory that they already have. The reason this works is because at every location other than location I, Alice and Bob will have shares of 0, so effectively they'll only be re-randomizing their existing XOR shares, not changing the value they correspond to. On the other hand, at location I, they'll effectively be XORing in v delta, updating that element to the one they wish to write. So now we have a scheme that can read and a scheme that can write, but they use different underlying memory formats, so we need to find some way to do a conversion between them. And the conversion method is also surprisingly simple. Once again, we have XOR shares, but we need identical encryptions, and this is how we're going to acquire them. Alice and Bob will each choose some new ROM encryption key, which is private to each of them. They then iterate over their secret shares of the memory, encrypting those shares element by element. They then swap their encrypted shares such that both Alice and Bob have two different encryptions of two different secret shares under two different keys. Finally, they XOR these encrypted shares together to produce a single, doubly encrypted read-only memory. And they pass their encryption keys back to the secure computation such that this memory can be decrypted later during the read. Better? Oh, wow, it did go out. There's another piece that's bound by multi-party computation, and in this region we find that our scheme is a factor of 10 better than both square root ORAM and circuit ORAM for part of its parameter regime. Indeed, it's better than both solutions over most swaths of parameters, although there is some small region where square root ORAM outperforms us. We do even better in terms of the communication expended during an access, improving over circuit ORAM and square root ORAM by a factor of up to 20. Concretely, we use the same amount of communication at 2 to the 32 elements, as circuit ORAM does at only 2 to the 15 elements. Finally, because we can use the refresh mechanism outlined earlier to initialize our ORAM, not only is our initialization procedure asymptotically better than the best previous result, it also leads to a factor of 5,000 practical improvement over some parameter regimes. Finally, I should note that our ORAM has extremely low memory overhead because it needs to store only 2 copies of its underlying memory, one for reading and one for writing. And these are stored at their native size with no expansion. Consequently, we're able to instantiate ORAMs 256 times larger than the ORAMs we were able to instantiate with circuit ORAM on similar hardware. And we believe that square root ORAM should be similarly limited to within a couple orders of magnitude. In addition to the binary search benchmark I showed you guys a little while ago, we also reran the stable matching benchmark that was presented at CCS last year and found that our scheme yielded a factor of 2 improvement in terms of both execution time and the number of non-free gates expended. This in spite of the fact that the ORAM in question had less than 5,000 elements and the algorithm had more than n squared ORAM accesses, effectively nullifying any advantage that our initialization procedure could have given us. Finally, I should say a few words about the title. We've called this work Scaling ORAM. This is a multiple reference. On the one hand, it is true that we are able to instantiate ORAMs at a significantly larger scale than any prior work would allow. Concretely, we were able to instantiate ORAMs with internal sizes of 16 gigabytes on machines with physical memory sizes of only 120 gigabytes. By comparison, with circuit ORAM, we were only able to achieve 64 megabyte ORAMs on the same machines. Although it should be noted that the circuit ORAM implementation we used was optimized for speed, not for memory usage. Although, for that matter, so was our algorithm. On the other hand, however, our title also refers to the fact that we believe that this is an ORAM that can scale. And this is what I mean by that. Ultimately, our scheme is bottlenecked by the linear region, way off to the right over there. Fortunately for us, however, this linear region is due to local computation. And so I don't have any theory for you, but I do have an answer. First of all, I believe there was at least one prior work that thought about optimizing initialization. That would be the ORAM scheme by Zeher et al., I thought I saw him sitting back there a minute ago, but maybe not. That's the one that produced a 100-fold improvement over circuit ORAM. But to answer the question about whether or not this is inherent, to some extent, I think so for ORAMs that store their data elements out of order. Obviously, if your ORAM storage is going to be out of order, then you're going to have to expend some time shuffling it. And if you can't reveal the shuffling pattern, then you have to expend a lot of time shuffling it. That said, there may be other schemes that also have asymptotically optimal initialization. I just don't know of them. Yes, the shuffling, or with some schemes that we didn't know how to do anything other than write each element individually. I believe actually that has also been improved upon. I think there's now a much more efficient initialization for circuit ORAM, but I think it only achieves performance maybe on par with square root ORAM's initialization. Anyone else? Oh, you have a question. Okay.
You're talking about this technique in the secure computation setting, but can the idea be readily applied to non-secure computation setting, like the same scenario that the first talk was covering, where you have multiple non-including servers and just want to do normal ORAM? Does this idea ready out of the box to work in that setting? And how would you think the performance will compare with the first one?
So to answer that, it is ready out of the box in the sense that, of course, you can make this technically work. It's a slightly weaker security because you don't have to hide the client. And we should expect that the performance is probably quite a bit better than it was in this talk because we no longer have to run the client as a secure computation. That said, I haven't specifically evaluated this scenario. If you're willing to accept this security model in the outsourcing scenario, I'd be very curious to see how it performed. My question, though, would be whether or not you can do something better, because in the outsourcing model, things like AES are really cheap, so you don't have to jump through a whole bunch of hoops to reduce your computation. So all that to say, I don't really know. This might be useful in the outsourcing model. In fact, there's reason to suspect that that's even likely over some parameter regimes, but probably not in general. Anyone else? Okay, so since no one asked the questions, I have a couple bonus slides for you anyway. So here's a cost breakdown of our scheme. You see 4 lines here. The top 2 are at 2 to the 30 ORAM elements, and the bottom 2 are at 2 to the 20 ORAM elements. And in each pair, the top one is the standard FSS algorithm. That is the one that runs the pseudorandom generator in secure computation. And the bottom 2 lines the bottom lines in each pair are the ones that do our optimization with no pseudorandom generator. And the point of showing this is, A, to demonstrate that this optimization actually makes a huge difference, right? If you look at the bottom pair at 2 to the 20, you can see that this is a dramatic reduction in cost simply because running those AES calculations inside of MPC was really expensive. On the other hand, when you have 2 to the 30 elements, the secure computation is no longer the bottleneck. Now it's the local computation. So in these scenarios, it actually makes sense just to run AES inside of MPC. Furthermore, we can achieve a constant number of rounds if we don't use our optimization, which may be useful in scenarios with very high latency. The second thing I would like to point out is I mentioned early at the beginning that actually the cost of doing the stash scan, that square root of n cost, is negligible. And this basically illustrates that fact. The stash scan is the red region. And as you can see, at 2 to the 20, it's pretty negligible compared to everything else. And at 2 to the 30, again, it's nowhere near the cost of doing the local computation. Because additionally, we can actually do things in parallel. Because we can do local computation at the same time we're doing secure computation, we're actually able to hide the stash scan entirely. Nonetheless, if you were to optimize this enough, it's reasonable to believe that you could eventually find a parameter regime where it's possible to detect the presence of the stash. It might take a lot of work, but hey, it might happen someday. And for those scenarios, it's not talked about in the paper, but we believe we actually have a way to make this ORAM stash recursive, which would increase it or would improve its asymptotic performance even more so. The question is sort of, in practice, does it matter? Would it actually improve things? And at least today, the answer is no. And that's all I have. So thank you for coming. Happy Halloween.